Oh my Lord. Okay. All right. So we're on page 9 talking about compound interest and the number E. So completely different setup than what we've been doing, but at the same time, very similar. So with compound interest, it typically deals with money. All right. So you'll usually see these in terms of bank situations, things like that. So first things first, let's just kind of look at a warm up here. If $500 is invested at 4% annual interest rate, how much is in the account after 1 year, 5 years, and 20 years? So, since it says annual, we can just assume that this is an exponential growth problem. So we're just going to say it's a growth problem, which who remembers the formula for growth? So this is 2.2a. Look back at your notes if you need to. Who remembers the formula for growth? Right. So your accumulated value is equal to your principal or your initial value times 1 plus r, which is your rate of increase or decrease, all raised to the t power, which is time. So if we're looking at this problem, what's my initial? 500. So we'd start this out as 500 times 1 plus, what's my rate of increase? 4%. What's that as a decimal? 0.04. All raised to the t power. Now, it then wants us to find out how much happens after 1 year, 5 years, and 20 years. So you may want a calculator for this. Because all we're going to do is plug in 1, 5, and 20 in for t and see what we get. So take a minute, plug that into your calculator. Let's say round to the nearest cent, so 2 decimal places. So we're going off of 2 decimal places. All right, does anyone have for me when t is equal to 1? How much money do you get? Landon? 520. Is there any change? Or is that just it? Okay. So after 1 year, we have $520. Someone else. What's 5? Tomas.
608.
Say that one more time. 608.32. So that's how many we have after 5 years. All right. Someone else? Tell me 20. Jasmine. So it's 1,905, you said? 1,095. Good. So that's how much money we would have in our account after that many years. So that's not how much money we gain. That's how much money is actually in our account. All right. If we want to know how much money we made in interest, we just take the amount of money we have, subtract 500 from it. That's how much we made in interest. Yeah, this is
Instead of 30, 39,
33. All right. Now that's just a warm up. So the problem with that is that who's ever dealt with banks before and interest rates? Like, have you guys ever dealt with kind of with interest rates with banks? Like, if you opened a savings account or something, a lot of times you do not gain interest rates by year. It's typically by month, semi-annually, quarterly, whatever. All right. It's not necessarily always annually or by year or per year. Now, that's where the compound interest formula comes into play. So the compound interest formula is this right here. It looks like a pretty big formula, but it's really not that different from the exponential growth formula. It just adds in an extra thing, and that's the n value. So A is still your final amount, just like it was with exponential growth. P is still your principal or your initial, just like it was with exponential growth. R is still your interest rate. All right. And again, it still has a decimal. T is still your number of years. So, number of years that have passed. Now, here's where it differs right here. N. N is the number of times it is compounded. And what that means is it's how many times a year that interest rate is taken. So, for example, if I said I took your interest rate annually, how many times a year is that? Once. So, once per year. What if I said semi-annually? That's twice per year. I would write this down because these are words that you will definitely see. What about if I said quarterly? That's 4 times a year. And then the last one you'll see is monthly. So if you're doing monthly, how many times is that a year? 12. So essentially, your n value would be one of these numbers depending on how many times they take it per year. So if it says monthly, your n value is 12. If it says semi-annually, your n value is 2. Quarterly, your n value is 4. Annually, your n value is 1. All right, that's the only difference between the compound interest formula and the exponential growth formula. All right, if you notice, the exponential growth formula usually works with annual, which if you look, if you raise everything to the first power, so if we replace n with 1 here and 1 here, what do we essentially get if we put n equals 1 for those parts? So think about what's r divided by 1? R. What's t times 1? T. So when n is equal to 1, we still have a equals p times 1 plus r raised to the t power, or your exponential growth. But that's only when n is equal to 1. Any other number, we still got to use that formula. All right, so let's do some examples here. So again, use this formula when you're calculating interest earned in an account more often than once per year. If it's more than once per year, use this formula. If it's just once per year, just use the exponential growth formula. All right, because again, you would get that anyway if you plug in for one. Not saying you have to, because again, you'll still get the same thing. So let's look at an example. So again, for example, some accounts earn interest monthly. That is 12 times per year. So the annual interest rate has to be divided by 12, and the exponent t years has to be multiplied by 12 to represent the calculated 12 times per year. All right, that's basically what I just said earlier. So monthly, 12 times per year, and that's your end value. So now let's look at a similar example to what we just did up top. So what would happen to $500 invested at 4% interest if it's compounded monthly? All right. So first off, let's just set up the formula before we start putting things in our calculator. So if we're compounded monthly, that means my end value has to be equal to what? 12. Compounded monthly, once every month. There's 12 months in a year. So that means my end value is equal to 12. What's my P equal to? So remember, P is your initial. 500 is your initial. That's how much you invested. All right. What about your R value? What is that? 0.04. That's your percent rate as a decimal. So I'm just going to plug it into this highlighted formula up top, the highlight green formula. So I have A is equal to 500 times 1 plus 0.04 divided by 12. I'll put parentheses around that. All raised to the t power. Guys, if you need to turn off the light, I know that's really light. All right. Now, we're going to use this formula to determine how much we have in our account after 1 year, 5 years, and 20 years. Oh, I almost forgot. This is 12t. It's n times t. So we're finding when t is equal to 1, t is equal to 5, and t is equal to 20. So be careful when you're plugging this in. I highly recommend you put parentheses around here when you plug it in, as well as here and here. Basically, plug it in exactly as you see it in your calculator. Just be careful about those parentheses. So take a minute, use that formula that we just made up, plug it in for t equals 1, t equals 5, and t equals 20, and get some values. So again, you're just plugging in your calculator, and I'll do t equals 1 as an example if you're struggling with putting it in your calculator. So you would type in 500 times 1 plus, I'll do parentheses, 0.04 divided by 12, close the parentheses, parentheses again, all raised to 12 times 1. And make that extra parenthesis. Hit enter. So you should get like 520 and some change. So 520 and 37 cents. Now, let me show you a trick so that you don't have to constantly keep typing stuff in. All right. So I don't want to retype all of that in. All right. It takes a minute. If you're pretty much using the same entry, but changing like one number, if you hit second, so the blue second key, and then enter, it re-inputs the entire entry. Then you can use your arrow keys and change this 1, because that's the only number. If it's hovering over it, change that 1 to 5. Then hit enter. And I now got the second, 610.50. So that's kind of a little speed thing. If you hit second and then enter, it'll re-input whatever entry you had previously, and then you can just change that one number by using your arrow keys. So if I do that for 20, second enter, use my arrow keys, do 20, put another parenthesis at the end, hit enter, get a 1,111.29. Is that what you guys got when you put in your calculator? Now, how did that compare to what we did up top? What kind of happened? So what's the difference between these values that we did here at the beginning and these new values that we got? What do you notice? What's more money? Right, when we're compounding monthly, it's more money. We end up with more money. Why do you think that is? Anyone got an idea? Someone who hasn't talked today. Why do you think if we compound monthly, we end up with more money than if we compounded yearly? Right, because you're essentially just doing it more times. You're doing the 4% more times. All right. So that's why if you compound monthly or every 6 months, you actually make a little bit more money than you would per year because it's doing it more. All right. So it builds up a bit more. So compound monthly gives us more money than annually. All right. That's essentially what happens. The more times you inflict or take that interest rate, more likely than not, you'll make a little bit more money because it happens more often. Now, let's try some more examples. Let's look at letter A. So let's set this up. $1,000 are invested at 3% compounded quarterly for 5 years. So let's figure out my different parts first. So what would my principal be? Or my initial value? 1,000. What would my R value be? 0.03. Your R value comes from the 3%, and you just convert it to a decimal. What's my T value? T, not N. 5. It's the number of times that you're doing it per a year. Or how many years have passed, I should say. Now, what would your N be? 4. That's where the quarterly comes in. So your N is where the quarterly comes in, which means 4 times per year. Now we're just going to plug it in to our formula. So A equals 1,000 times 1 plus 0.03 divided by 4, all raised to the power of 4 times 5. All right, take a minute, put that in your calculator, see what you get. All right, anyone got an answer yet?
1431.31.
Say that one more time.
1431.31.
1431.31, right? 41. So 1431.41. Did anyone get something different? Or yeah, that was what I got initially. You may just put something wrong in your calculator, Tomas. It may just been like one sign messed up. So yeah, it should be $1,161.18. That's an approximate estimation of what we get. Now, we're not going to do letter B, but I want to ask you guys this. Something we haven't seen yet. Compounded daily. Think about this for a second in terms of a year. What do you think your end value means if it's compounded daily? What would your end value be if it's compounded daily? Say it again. 365. Because if it's compounded per day in a year, there's 365 days in a year. So you'd still set it up like we did in part A, but your end value would be 365. All right. Now, the next page is a nice little chart that you can use to kind of help you figure out how you write these formulas based off of how they're compounded. So compounded quarterly, that means your end value is 1. So you'd have P times 1 plus R to the T. So just the exponential growth formula. Now, then you would have P for quarterly, P times 1 plus R over 4 raised to the 4T. Monthly N is 12. So you have P times 1 plus R over 12 times 12T. Daily, your N is 365, so it's P times 1 plus R over 365 times, raise that, yeah. Now, what do you think your N value would be hourly? How many hours in a year? Think about it. How many hours are in a day? How many days are in a year? So what's 24 times 365? 8,760. That's how many hours are in a year. So it'd be P times 1 plus R all over 8,760 raised to the 8,760T. What about every minute? How many minutes? How many minutes in an hour? So just multiply 8,760 by 60. Right, it'd be 525,600. So it'll be P times 1 plus R over 525,600. All raised to the 525,600. All right. What about every second? So how many seconds in a minute? So multiply 525,600 by 60. So yeah, this one's in the millions. So 31,560,000. Now you will not be asked something like this, but this is just kind of for fun. All right. But essentially, if you don't remember, and then it's all raised to all that loveliness, because I'm not rewriting that. So if you don't remember how to figure out like daily, for example, you know that if you're talking about per day, you just think, okay, how many days in a year? If they then ask you hourly, they may ask you hourly. Hourly does pop up every once in a while. All right. All you do is take the number of days in a year, and there's 24 hours in a day. So just multiply 360 by 24. All right. That's just converting measurements of time. Now, the last rule that we have is used for something that we call compounded continuously. And it means a little certain thing. For that, we have this very special number called E. Now, I'm not talking about a variable E. E represents a number. It's very similar to pi. So if you see a lowercase e in this class, more often than not, it's referring to a number. So E is similar to pi. It equals a fixed number. All right. And you can calculate E in your calculator. So if you look in your calculator, if you hit second and then the division symbol, you get E. Hit enter, that's what E is worth. It's like 2.718 and goes on forever and ever, just like pi. All right. So again, it is a number like pi. It's a fixed number that some guy named Euler back in the day, he's like a math guru that every mathematician follows. Euler, there's Euler method. But essentially, he named it E because his last name starts with an E. And when you come up with something, you get to name it however the heck you want. All right. So E, it just represents a number. So don't be confused because it does sometimes look like a variable. It's not. It's a number. All right. It does have value. Now, Euler came up with this because a lot of times back in the day, like long ago, before there was like the modern calculators and computers and all that stuff, where you just had a bunch of old guys in wigs sitting around in togas figuring out math stuff because they're just bored that way. All right. Well, they probably also just want money. So, these guys would get stuck with a problem, or they just keep seeing this pattern coming up. They're like, okay, this number keeps coming up. What is this number? That's how pi came about. That's how E came about. They just kept seeing these numbers in different processes they were doing. And they're like, why does this number keep coming up? There's got to be some consistency here. All right. That's how pi came about. That's how E came about. All right. Pi came about because when they were dealing with circles, they noticed that the number pi, or 3.1415, blah, 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 kept coming about. That kept kind of getting in your answer. Same thing with E, but it was mostly used for exponentials. All right. They just kept coming about. So when you see the letter E in this class from now on, it is a number. It's also a base. So E is used as a base in modeling exponential situations that involve continuous growth or decay. So a lot of times this represents cell reproduction, population growth, decay, value of a car, radioactive decay, lots of things. A lot of times it will flat out say the word compounded continuously. The formula for compounded continuously is A equals PE raised to the RT. And the way a lot of students remember it is that they remember the word PERT. All right. So A times P, or A equals P times the number E raised to the RT, where P, R, and T are the same things that we've been talking about. P is your initial, R is your rate, T is your time. And again, you only use this formula because a lot of people, as soon as they learn this formula, they're like, oh, this formula is so easy to remember. It can only be used in one situation. The only situation when you can use this formula is if it explicitly says compounded continuously. Keyword, continuously. All right. If it does not say continuously, do not use PERT. All right. If it does not explicitly say compounded continuously, do not use PERT. You're probably using another formula. All right. This unit is a lot about formulas. Now, I do want to try one example where we are looking at compounded continuously, just so you can see what it is. So look at page 11 and look at number 1, letter E. So basically what they want us to do for number 1 with letter E is they just wanted us to figure out the different amount of money that we earn when we compound in different ways. I want to look at the one where we're compounding, when we're compounding continuously. So amount of money you'll have after 10 years if 15,000 is invested and the accounts are 6% interest compounded, however. So in this case, 6% interest compounded continuously. So remember, if you're compounding continuously, you are using PERT. And again, I like to put parentheses around the E just so I know that's a number. All right? Just so I know, okay, I'm not replacing E with anything. It's a number. And again, your calculator will calculate E. You don't need to put in like a rounded decimal or anything. Your calculator has the capabilities of putting E in for you. All right? Now, let's figure out the rest of my stuff. So what's my P value here? What do I start with in this scenario? 15,000. What's my R in this case? 0.06 or 6%. What about T? How many years have gone by? 10. So I'm just going to replace all of these into my formula. So I have A is equal to 1,500 E, all raised to the 0.06 times 10. All right, that's all I did. And you will put this exactly as you see it in your calculator. So in your calculator, you're going to type 1,500. Now, there's 2 ways you can get E in your calculator. You can either do second division symbol like I did, or if you don't want to have to worry about hitting the exponent sign, hit second. And then do you see on your calculator to the left of the number 4 where it says LN? All right, hit that button. It'll insert E as well as a decimal place. So if you need E without a decimal place, hit second division key. If you want E with, not a decimal, exponent place. If you want E with an exponent, hit second ln. And then I'll do 0.06 times 10. Hit enter. That's the number we get. So again, to get E where it's raising it to a power, just hit second and then the ln key. And again, the ln key is to the left of the number 4 key. So this would be about $27,331.78. Any questions on how to use compounding? Yes. So we always say approximate because technically, if we ever round, it is an approximation. It's not the exact value. So if you ever see a bunch of decimal places and I tell you to round to the nearest cent, you gotta say approximation. So that's technically, I won't take off points if you say equal, but get into the habit of making approximations because you gotta know in your mind, okay, this is an approximation. It's not the exact. We don't get exactly $27,331.78. That's the approximation of it. All right. So it's more just me being a mathematical stickler, but it's a good habit to get into when you're rounding. All right. Any questions on this? All right. So we're going to stop here today. Now, there is a delta math that combines everything that we learned from 2.2. So 2.2 A, B, and C all in one delta math. It should already be open. You guys got a solid 45 minutes to do this. All right. So you can probably knock it out during class. You can also use this as a time to make up any delta maths. The classwork for this one is basically just pages 11 and 12, I believe. That's the classwork for this. Yeah, 11 and 12. So just finish up pages 11 and 12 for packet work. But I recommend working on the delta math first.